Okay, I guess it's me. So, remember that this chapter is going to be an overview for spectroscopies. That's why we sort of dart around between like UV, IR, different types of spectroscopy. Okay? So for IR, your cells have to be made of some sort of salt. So if you try to use for IR things like glass, fused silica, anything with covalent bonds, they're going to have very large absorption bands within the regions that you need to use for IR. Salts typically have absorption bands where they'd absorb light up in the 6,000 wave number region. Okay, and for reference, IR typically happens between the 4,000 something wave number region down to about 400-ish, depends on what you use. Like for example, NaCl and NaBr can only go down to like 600, 700 wave numbers. Okay. By the way, if you ever take a background, that overall like concave looking structure that you see in a background for IR, that's actually your salt. That's your windows. Okay? And where it's going down is where it's absorbing a lot, so you get a much worse signal there. So your limits of detection are much worse there. Okay? Your dynamic response is also much worse. All right, so there are a few different ways to do solid samples. You will notice that ATIR, which is what we typically use in the lab. Remember the ATIR? Remember the IR in the lab where you just put stuff on a window and clamp down on it? Okay, you can put liquids or solids, it doesn't really matter. That doesn't get a lot of love or coverage in books. And because that's a newer method, and so it doesn't get put in books a lot. But just it's been taken into the mainstream, and it gets used a lot in not analytical labs, but in more qualitative labs. Okay? ATIR is not a particularly great method to use for analytical, okay, qualitative experiments. And one of the major reasons for that is each time you put something down on it, you actually should wait for it to settle out. Otherwise, it doesn't evenly settle across the window. And so you always get slightly different spectra. Yeah. And so there's a whole technique to that, but most of the time when you're talking analytically, you're going to be using other techniques, okay? It would not be, most of them are not ATIR methods because it's not particularly reliable. There is methods of improving it, and you can get pretty good actually, but we can teach a class on that probably. If you guys are ever curious, come and talk to me, okay? Okay. So this is one method that you can do solids, and you'll actually see I have out on the tray a mineral oil to do this with, if you're curious. So the solid samples are ground into fine powder. You can then add mineral oil, neutral. Excuse me. Excuse me. This will give you a dispersion. That dispersion of powder in mineral oil is called mule. That's actually pressed them between two plates. You can use actually quite a few different varieties of plates. KBR is the most common because it's both pretty cheap, but it also has a very nice spectral window and works very nicely, okay? NaCl, NaBr windows these are the cheap windows that work okay, okay? But anything that has any sort of moisture content is going to erode these windows, all right? By the way, like a cylinder like this, yeah, it doesn't have any windows here. Okay. These gas cylinders in IR would have like an NaCl, NaBr, cesium. The better windows, by the way, are cesium salts. They feel kind of soapy. They have about the same consistency and feel as like a bar of soap. So they're very soft. They're very expensive. They're like $400 a plate. So one of these cells would cost you $800. There's a really funny story if you guys want to hear it sometime involving disappearing windows and people not understanding things. Let me ask you guys a question. All of these are salts, right? What do you think happens if you try to wash these windows with water? They'll dissolve, right? So there's a graduate student that washed those very high-end cesium salt plates, which were closer to $800 per window. And how you actually treat them and get them so they're smooth again, because they do erode over time if you use stuff. They can do the moisture in the air. They can slightly get wavy on the surface because moisture dissolves it and then replates it out as it evaporates. Anyways, they corrode over time. They get worse over time. You have to smooth them. It's called polishing them. And what you do is you put absolute ethanol with a chromium oxide agent, a chromium, not the 6+, okay? Because that's highly toxic. It's that green powder that they put in vitamins. You put that together as a mule and immersion, and then you take that with a cloth and you essentially rub that around on your window like you're polishing like a car or boots, okay? And that would polish the surface so you get nice smooth surfaces and you get good spectra again. There's a graduate student that did not understand this, and so he tried to clean these with soap and water, left them soaking in soap water. He runs up to the advisor. This is my advisor that I was under. This was not me, though. This happened before I was there. And so he runs up to the advisor like a half an hour later going, "Somebody stole my windows." And so the advisor comes down and goes, "What is that?" And he goes, "Soap and water." And that's salt. You dissolve the fucking things. You imagine. There goes $1,600. Oh, man. Anyways, you would press this between two KBR plates. KBR typically is a bit more scratch resistant, which is why you'd use KBR here, by the way. And then you would take the spectra by passing the beam through it. Okay? By the way, this right here, these small millimeter path length ones, look a lot like what this looks like. Okay? It's literally like making a slide. It's just up and down instead of sideways. Okay? Then you pass the beam through. The single beam spectrometer is only going to have one beam of light. That's what makes it a single beam. That's like most spectrometers you've probably seen. I don't think you guys have actually ever seen a double beam spectrometer. Okay? We measure the irradiance of the light that's passing through a reference blank. You guys actually learned this the other day, right? Remember, you put in that reference, your blank, you pass the beam through it, and then you use that as 100%, the P0, right? Okay. The cuvette is removed, and it's replaced by an identical one containing the sample, and you guys did that with making a Beer's Law, and then you made a sample one, right? So those are all types of samples. Some of them were standards, whereas some of them were samples from a pill, right? Okay. So the irradiance of the light would then pass through the sample. This irradiance is measured as P. So how does that differ with a double beam spectrometer? So a double beam spectrophotometer splits the light alternatingly between the sample and the reference cuvettes. Most of them do this very fast, by the way. Okay? And so it looks like you have a constant beam of light between them. You can't see that it's flickering back and forth. All right? When recording an absorbance spectrum, first you'd record the baseline spectrum, and this will be subtracted from the sample's absorbance. And that's actually literally what happened when you took that background, the 100%. Literally, it was taking that number, whatever absorbance, that matrix, that blank had, and it is subtracting it from the absorbance of your next samples. Okay? By the way, that's why your number was negative for those. You had set your background as something that had a higher absorbance. Probably took your background from one of your other samples, one of your higher concentration samples with the RNN. Does that make sense? Okay. Yeah. So you'll choose the wavelength of the maximum absorbance when you're doing something that can't select wavelengths rapidly. For example, like the spectrometers you guys used for the UV visible light spectrometers you guys used. Okay? I believe those can actually go slightly into the UV as well. Anyways, so you selected a wavelength, right? Why do you do the wavelength of maximum absorbance? Well, there's three things you always have to keep in mind and be aware of, right? Every time you do a spectra, there is your dynamic range, right? So that's the maximum concentration that you could do spectra with, okay? Then there's your limits of detection, right? And finally, there's how that scales. So let's think about it like this, okay? The windows, we consider those clear, right? But are the windows actually clear? No. We consider air clear, right? But is it actually clear? No. And we know that because when we look up at the sky, it looks blue, doesn't it? So what's happening? Well, that's actually bending light. It's called the Raman effect. And it's actually changing the color of the light because of the scattering, okay? It's essentially, you get hit by two beams of light at the same, or you have energy in your molecule, the beam of light hits it, and instead of re-emitting the exact same frequency, you add the energy that was already there and re-emit it, okay? Or subtract it off, one of the ways. Depends on which way you're looking at for the Raman effect. But that's beyond the scope of this discussion. So what do we see here? Well, we need a huge amount of atmosphere to see its effect, don't we? Okay? And so a little change in concentration for the atmosphere is going to give us no effect, right? We won't be able to see it. Whereas if we use something that absorbs very well, then even a small change will give us a large effect, right? Does that make sense? Okay. So this is why the analysis will have the greatest sensitivity at the maximum absorbance. There's also little variation in the absorbance versus the wavelength at this maximum absorbance. When you're doing a spectra that you want a quantitative result from, you really need your absorbances to stay somewhere in the range of 0.4 to 0.9 is ideal, okay? That's going to give you the best effect. When they fall outside the range of 0.4 and 0.9, you're going to get less accuracy. So too much light absorbed makes the intensity hard to measure. Too little light absorbed makes it hard to distinguish between the blank and the samples. The less noise, the lower concentration of analyte that can be detected. By the way, this is why we went ahead and went down a bit more. Like, this is our rough range. If you have less noise in your spectra, like our visible light spectrometers that we used, you can go down more. And so we went down to like a 0.1, right? And you notice that you didn't have it didn't have any noise at all, did it? Like, it wasn't bouncing up and down, it wasn't moving around, was it? Yeah. When you went back to it, you got the same damn number every time, didn't you? Yeah. Did you guys ever use those crappy visible light spectrometers, the little boxes that hook up to the... Yeah. You never used them? Okay, yeah, you used it, but he didn't, apparently. So those things are just terrible spectrometers. Absolutely awful. If you were to take the same sample, what you'll see is you'll actually have a change in like the 0.01 area or 0.008-ish area. And they'll bounce around. And so that has a lot of noise. You place the cuvettes into the instrument reproducibly and wipe off fingerprints and dust. Remember when I came in and I was like, use the same cuvette, rinse it out with the lower concentration ones. This is why. You gotta reproducibly do this. Okay?
So you said you'll use the different cuvettes to match set.
Yes.
How would you be able to figure it out?
Okay, so match sets are produced and they're sold as such. And okay, there's two. How you actually figure that out is you would take them and you literally just take the same sample sets and run them. And remember where we did the stats, chapter 4? That determining whether it's the same data set, that is that. That's what you do. You take a bunch of data points with the same samples in each one, A, B, group A, group B, and you'd see if they're actually different or not, and within what error limits they're different. That makes sense? Yeah. That's done, typically labs don't do that though. What they do is they buy match sets, and another lab has done that. So the manufacturer has done that and given you the tolerances for that. And that's why I don't know if those are match sets or not sold with that spectrometer, is because no tolerances are there. Typically, they'd be in a little slip on the box. Like the box would have a little slip in it, and that would tell you the tolerances. Yeah, oh yeah. Yeah, if you guys want to do that, go for it. That would be a great one. Make sure you guys write some of these down, because I feel like we've said this like 20, 30 times now, and nobody ever remembers the labs you guys come up with. And I say, yeah, that'd be a good one. Maybe if you go back through all the videos, you can find one. All right. So this right here is your relative standard deviations versus the absorbances, okay? And so this is why you don't use very low and very high absorbances. So notice the relative standard deviations, as you go down in concentration, that spikes up hugely, right? Just like if you were to go on a balance and try to measure out 0.001 grams, right? You would get massive percent differences. Because, being off by 0.001 would be disaster. You'd be 100% relative error, right? And that's your breath. Oops, I exhaled. So once you get down past 0.1, usually this data is just worthless, okay? Absolutely worthless. And again, that would be somewhere around here, right? See, that's where it starts really going exponential. Okay. This is why the 0.4 to 0.9 is typically used. See how it's the lowest areas? Okay. As you get up past 1.5, remember how I told you that was your cutoff? Don't use anything past 1.5 on the visible light spectrometer. You start getting major increase too, okay? And this will actually start going up and up and up. So, okay, so we're looking at Beer's law for chemical analysis, which is good because you guys are going to be doing that, right? We're at actually the lab we should be at this point that you just finished like a week before. Well, should have finished a week before. All right, we're running a little bit late on everything. So for a compound to be analyzed by spectrophotometry, it must absorb light. This absorption should be distinguishable from that due to other substances in your sample. One of the places people fail on Beer's Law is they fail to pick a peak that they can distinguish from something else, okay? And you do need to be careful about this. What do I mean by that? If you were to take the full spectrum, you would see that some peaks are shoulders on other peaks. And this could be a shoulder on something else that you're taking, and then you won't get a nice change due to that peak, right? It'll be to whatever it's a shoulder on. Does everybody understand what I'm saying about a shoulder? It looks like your head and shoulders. So you have a bigger peak, and then you pick the smaller peak that's on it. Well, this peak's up and down, rise and fall, is not actually just due to the concentration, right? It's due to this other peak next to it moving. And that's why you always want to take your maximum absorption peaks when you do things like, visible light spectroscopy like we did, and are trying to make a Beer's Law curve, because then you don't have other stuff adding much to it. You get the least addition to it. Does that make sense? Okay, so let's do an example. Pure hexane has a negligible ultraviolet absorbance above a wavelength of 256 nanometers. A solution prepared by dissolving 25.8 milligrams of benzene in hexane and diluting to 250 milliliters had an absorption peak at 256 nanometers and an absorbance of 0.266 in a 1 centimeter cell. Find the molar absorptivity of benzene at this wavelength. So this you would just enter into Beer's Law. So do you remember your Beer's Law? So Beer's Law is absorbance equals molar extinction or molar absorptivity, which is what you're going to find, right? You have the absorbance right here. And then that's times your path length. Your path length's right there, right? It's 1. Good luck doing that math, huh? Times 1. Okay. And then you're going to take that times your concentration. And so your concentration is right here, isn't it? See that? So you have the amount you dissolved in it, and then you have the dilution. So you can get the molar concentration of that. You'd plug it in. You'd divide all your terms over, leaving you with the molar absorptivity on the right side. And that'd give you your answer, right? Does anybody have any questions on that? It's a pretty straightforward. Okay. So let's go ahead and look at a serum iron determination. So the serum iron determination has 3 steps. The first step is you need to get everything you're looking at in one species, right? And so you did something very similar to this, by the way. This is just an alternative way to do what you did, okay? So you would reduce all of your iron 3+ in this case to a transferrin, to an iron 2+. And so now we've gotten it all into one species. Now we're looking at the full amount of iron in that species, in that sample, right? As iron 2+. You'd add trichloric acetic acid. This would precipitate your proteins. This would leave you with the iron 2+ in solution. Why are you stripping out all these other proteins? Okay, so first off, you know this is serum, right? As in blood serum? Okay, so it has a bunch of different iron variants that are bound to various different proteins, right? It'll have iron 3+, iron 2+. You reduce the iron to iron 2+. Proteins typically have colors, don't they? Yeah, and they also absorb UV radiation. They absorb many different types of radiation. So you need to get rid of those other signals, right? So if you have all these other signals, this could interfere with your absorbance, right? And so you add the chloroacetic acid to precipitate your proteins. This will leave you with the iron 2+ in your solution. The next step is you would transfer a measured volume of supernatant liquid from your centrifuged mixture. You do the centrifuge to get your precipitate all at the bottom, so it'll stick nicely. Literally, so you can transfer that supernatant liquid out, right? So you transfer that to another vessel, a fresh vessel. You would then add buffer plus excess ferrozine to form a purple complex. Notice this part's very similar, isn't it, to what you did the other day? In fact, that's what you were doing. You were establishing a buffer. Remember, you dropping the drops in? You established a buffer. And then you added something to bind to the iron, right? That you can then measure its colorful complex. You always have to add excess of your binding agent so you can get, 99.999 something percent bound, right? Otherwise, you won't get, if you don't add excess, you won't get most of it bound. Okay, so in this case, we make a purple complex. That absorbance is going to be measured at 562 nanometers. That would be theoretically your maximum absorbance. This is the complex that's formed, by the way, in case you're curious. Right there. That would be your purple complex right there. This is what it looks like. You'll actually see that the serum copper also forms a colored complex with ferrozine. The interference is eliminated by adding neocuparin or thiourea. Here's the spectra right here. So if you add one of these two, these will bind the copper preferentially, and they won't be binding to your ferrozine and causing you to get that interference anymore. By the way, you guys notice that that's a masking agent? Remember when we talked about masking? All those same concepts are reappearing here, right? Yeah. Now we're just applying it to a specific type of analytical technique. Okay? All right, so again, these two agents bind preferentially to the copper. They form strong complexes. This will prevent the copper from reacting with ferrozine, which will prevent the copper from interfering in your visible light spectrum. Right here. Okay. So serum iron and standard iron solutions were analyzed as follows. So here's the steps to analyzing these. Step 1 is to add 1 milliliter sample, add 2 milliliters of reducing agent, and 2 milliliters of acid to reduce and release the iron from transferring. Notice that's that step where we get the iron from transferring, right? And we reduce it all to the same form, which is the iron 2+. Note that this is a very common trick to play to strip metals from various different transition metals, I should say, from various different binding agents, is you reduce or oxidize them depending on which one of the ones bind. Okay? So if it binds iron 3+, you'd reduce it, right? The iron 2+ won't bind them. Does that make sense? Cool trick, right? Okay. Step 2, precipitate the proteins with 1 milliliter of the 30% trichloroacetic acid. Centrifuge the mixture to remove the protein. This will leave you with the supernatant, which has the iron and other metals in it. Okay? Also will have copper, most likely. Step 3, transfer 4 milliliters of supernatant liquid to a fresh tube. You would then add 1 milliliter of a solution containing ferrozin and buffer. You would then measure the absorbance after 10 minutes. Step 4, you would establish each point on the calibration curve in the figure. You would use 1 milliliter of standard containing 2 to 9 micrograms of iron in place of serum. This number you come up with, this typically is easiest to come up with something that's in that range, okay? This is actually kind of a hard step to bridge. So if you kind of have an idea what you're going to be measuring, you can come up with a number range that should include what you're going to measure, right? And then you want those concentrations to fall within this range, okay? If you don't really have an idea what you're measuring, you're going to have to do some leg work at the beginning. So you'd come up with a giant range, and then you'd narrow it down, okay? This is showing you an already complete analytical technique where they're just measuring concentrations. They already have an idea what the concentrations will be, okay? But they're...
The standard containing 2 to 9 of iron, is that with the comparison to what the transferring would have had?
Yeah, so this is what this supernatant. The supernatant should fall within this range, okay? If it doesn't, you can still kind of get an idea what the concentration is, because the Beer's law curve does not end necessarily. It just won't be as accurate, okay? And so what you would typically want to do is either you would dilute this or concentrate it, make up a new solution if you can, or you'd make up a new set of standards. Okay?
How do you know which one to do? Or is it just like you choose?
Which is more expensive? Like, this being serum, you have limited sample for this, right? Because you probably took it from somebody. Yeah. And one of the reasons you do that, change the standard and check, is because you don't know necessarily where your dynamic region is with that instrument and with this set.
So,
okay?
Why would you be changing the standard? Like, what exactly is the standard being used to?
So the standard does several tasks for you. It makes your Beer's law curve. Okay, remember that? Yeah. And so you'll fit your Beer's law curve to this. But it also is what gives you the error of that Beer's law. Okay? So it's also checking, is that Beer's law fitting correctly? For example, let's think of this case, okay? We're fitting a Beer's law curve, right? So we plot our absorbance versus our concentrations, okay? So let's say my plot, I get points, point, point. Looks like a beautiful curve, right? Nice and linear. Beautiful, okay. Let's say I start going like this though. Ding, ding, ding. Yeah. Uh-oh. I got into my dynamic region now, and I'm past my dynamic region here, aren't I? Remember that? There's a linear region.
Yeah.
So if you do your standards, this will tell you where your limits of detection are. It will also tell you where you end your linear region and where you end your dynamic region. Okay? Because you know this concentration. You can test this, right? Your unknown, you don't know. You don't know if it should have been here, 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 wherever, right?
Yeah.
This, you know the next point needs to be up here, right? The next one needs to be up here.
So for the lab that we just did using the iron, we made, it was 4 standards, and then the one unknown, and we measured the unknown in comparison to the standards.
Yes. So the standards will make your Beer's law curve. Okay, and you're going to calculate an R squared, and that will give you an error for that curve.
Okay, so see how much iron is actually in it compared to the iron standard.
Yes. So you're going to plot the Beer's law. You can then use the absorbance from your unknown, and you literally just put that in the Beer's law. You'll have all the other terms, and you plug that in absorbance. and that'll give you the concentration. And then the error of that measurement is the error of your Beer's law curve. Okay?
That makes sense. I was just thinking it as like one standard, like you have like one standard that's being measured against like four unknowns.
No, another way around, yeah. You always need, and that's why I said you absolutely need at least 5 standards in case one is off. And you know, you can't ever drop below 3 because then you don't get accuracy.
So how many unknowns are you able to use for how many standards? Like, or is it usually only one unknown always? Or?
No, you can do as many as you want now. Like literally, we could have done 1 million unknowns. Like if we had wanted to, once we get our Beer's law established, and they all fall, as long as they all fall within that Beer's law, we could do 10 to the 23rd unknowns, whatever the hell you want. I mean, time-wise, you can't actually do that. But like, there's instruments that have like feeders on them. So there's like a Coca-Cola uses this. They use a ramen actually to do it. They have a specific peak they're looking at. They have a standard that runs at the beginning, and then they have literally a feeder, like a belt feeder, that feeds through millions of bottles a day. And what they're looking for is a peak to be a certain absorbance and fall on that, because they're looking at the concentrations of certain ingredients. And if the concentrations are off, then they remake the batch and get rid of it. I don't remember. I think that their instrument is so good now, because Raman spectroscopy, you can really get so damn good on one instrument that measures so fast. By the way, it's like, that thing measures thousands of samples a second. Literally, you can't even see the individual bottles. It looks like that. You know how a fan has that flickering effect, where you can't tell the individual blades? Looks like that. That's how fast that damn thing is. And if you get a good enough instrument, the electronics are good enough, you can essentially just load up a peak and calibrate it every like week or so. Because they won't change. So they probably only do it like every week or month or something, because they have a pretty reliable system, and you know, they're not looking at a like, you know, microgram. They're looking probably milligram at most. So they can have some error. That would be interesting, though, what exactly they use as a standard. They must have something. Yeah. I guess. Or just, you know, the last batch. Yeah. They could probably be using, you know, just a batch that they made that they know is right. It makes me wonder, though, if they try out a batch. Yeah, it tastes good. Oh, they'll freeze the whole batch.
Oh, just like stop.
Yeah. Yeah. The whole line freezes, and then they get rid of the whole fucking line. Oh, yeah.
Even if just one's off.
Yeah. Oh, yeah. That's actually pretty standard in production. Though there is a fair amount of that stuff that gets recycled and sold on to other things. So don't think they're just throwing it away and wasting it. But they won't sell it as Coca-Cola. Because, yeah, it would damage their brand, right? Anyways, no, that's actually useful, because that's a real job. Like, nobody realizes that there's teams of spectroscopists at every Coca-Cola plant. That's a job. Like, almost every production plant has a team of spectroscopists of some sort. Huh? Oh, same sort of thing. Yeah. Yeah. They do that for pretty much everything. The two major ways they do that is they either measure it in the bottle if they can, like glass bottles, that works really well, but or they take samples out of the batches. So what you'll see is like there's big like mixing containers at every, you know, somewhere along the step, and they typically have like a long straw-looking thing, kind of like one of the volumetric pipettes, but just, you know, really big and long. And then they like suck a little bit out and take a spectrum. And if the you know, there's something wrong with that, then they get rid of that badge. And they'd go a new one. And they try to figure out what the hell's going on. Anyways, this actually is valuable discussion. But yeah, there's so much here. It's unfortunate. Like, this is actually another course we could teach. It's called Instrumental. And then I could teach you a whole degree on it. I mean, honestly. So in this case right here, what we see is the blank absorbance was 0.038. Notice your blanks almost always have some sort of absorbance, right? Because your cell itself is not perfectly clear. Your solution is not perfectly clear. And then your matrix inside of that probably isn't perfectly clear either, is it? Especially the one we used for the iron, right? You notice that had a very definite color to it. Yeah. So this blank was this amount at 562 nanometers in a 1 centimeter cell. Your serum sample had an absorbance of 0.129. Notice that ideal and actual data are never quite the same, right? Remember, ideal range is like a 0.4 to 0.9. It's never going to happen. Like, it's a miracle if it ever happens, okay? However, you want to get at least like 0.1s for your sample. That would be reasonable, okay? Even the book does a great job of this because it's actual experimental data they use. And you never get the fucking ideal. That doesn't happen, okay? If you are getting ideal results, you should seriously think about what's going on, all right? Make sure that you have robust lab procedures to detect any errors, okay? Get nervous if you get ideal results. The blank was subtracted from each standard absorbance, so we would literally take that absorbance minus that we would get out of the instrument. The instrument does it automatically for us, actually. It takes that absorbance it gets minus this blank here, okay? So the least squares line through the standard points would be this, would be your least squares. Notice it's a linear line. It looks a bit like a Beer's law, but it will never actually be exactly like the Beer's law because it always have a y-intercept. And the y-intercept should never actually be 0, it should be something close to 0, okay? Because this is real data, right? You're never actually going to be on 0. There's always going to be some light that's scattered and you couldn't get, okay? If it is 0, you know something went wrong because you're screwing up.
So is the blank y-intercept, or is it just based on, or is blank
Yeah.
just
If you did not take this blank, it would be added into the y-intercept. Yeah. And, I mean, it's not just the error of the blank in the y-intercept. There's also other errors in there. Typically, this gives you systematic errors. But yeah. But it can be a random error, just caused a small difference. Like systematic errors will make this a pretty decent difference. And then you know your procedure's wrong somewhere, right? Something like this, when you're looking at 0.1 values and you get 0.0015, 100 times lower, that's probably a random error. It could change as you add more standards to it, okay? The more standards you get, the closer this should get to 0. But you typically only do like 5 or 6 because it takes a while, right? Making all those damn solutions takes time, and doing it takes time, and you know it's not the easiest thing in the world. This is a Beer's law graph, by the way. Notice the concentrations can be pretty much anything you want. So this is micrograms per 250 milliliters or whatever they dissolved it in. This is the absorbance. This is your standards right here. Notice they're a little off the line because there's always error, right? Okay. Interestingly enough, this actually gives you a This actually looks like it might be curving this way, which is what we were talking about. And notice this is at the 0.9. So it makes me wonder if they did the next one, if it would be like here. And that's your end of your dynamic region. But whatever, right? Obviously, this is a good Beer's law. Okay.
So how do they know which
This is the maximum absorbance. So you would go through and find the largest one. Ideally, it would be off on its own without any large peaks next to it. Okay. So doing the maximum absorbance is going to minimize any interference from other peaks. Though if you have two that are very close together and also very large absorbances, you'd be better off not using that. You'd be better off moving off onto something that's off by itself. Okay? But again, you always have to make compromises. Okay? Usually it's the peak of maximum absorbance, because visible light spectroscopy is not particularly complex compared to other things like microwave or infrared. Okay. Does anybody have any questions about this so far? All right, so you're going to monitor changes in absorbance during a titration to determine when the equivalence point has been reached. This is actually a pretty common way to do titrations, where instead of depending on your eyes to monitor some sort of arbitrary color change, which remember when we did all those like, when would this change calculations? We always use 10 times the concentration, right? 10 times the concentration's a lot. That's actually pretty far off the equivalence point, right? Like, if you really think about it, that's a really far distance compared to when we've normally been doing things, right? And so you can do this also with spectroscopic. You can also get really complex in your setups. So remember we were talking about gram plots, right? And so you can actually use this spectroscopy with a Beer's law to determine the concentrations as you do the titration. So literally add some. This is the new concentration. And you can even do standards like that. So you can do a lot of complex stuff. Like, these are not independent concepts that never merge together. This whole course is building up to give you tool sets that you can merge together to do, complex measurements. Okay? Or very accurate measurements, one of the two. So a solution of iron transport protein, transferrin, this can be titrated against iron to measure the transferrin content. Each transferrin molecule would bind to iron 3+ ions. The transferrin without iron is colorless. This is called apotransferrin. When the iron 3+ binds to the protein, a red color, with an absorbance maxima, wavelength of 465 nanometers. Remember that the color you see is the opposite color to the color it absorbs. Okay? Because what you see is what it releases, right? So this is the aptotransferrin going to transferrin, which is red, right there. That's that equation. And so literally you would add this iron 3+ to this transferrin. As you add it, it would develop more and more height. The height of this little area would be a better measure, but you get the idea. Height. The absorbance would increase, right? As your concentration of the iron increases. And when you hit a maxima, that's going to be the maxima of the transferrin, right? Isn't that neat? It's a spectroscopic titration. You can also do this with purifications, by the way, in case you're curious. All right, so the titration of 2 milliliters of apotransferrin with 1.79 millimolar ferric nitrillo triacetate is this figure right here. This is your corrected absorbances versus the microliters of the iron 3 plus added. You notice you get a nice linear relationship here, and then that relationship changes right there, right? Okay. The changeover is your endpoint. What's happening is this is the linear portion of the binding. Remember, bindings are always logarithmic, right? Okay. And then this is that changeover to the logarithmic portion of the binding. Okay? And so right there, that's your endpoint. Cool, huh? Okay, let me go and finish this and I'll go on to the next one, and then we'll stop. So again, iron is added to the protein, the red color develops, the absorbance will increase. When the protein is saturated with iron, no more combined, and the curve is going to level off. It's not actually true that no more combined, but essentially you have the vast majority of the binding spots bound. Okay. The extrapolation of the titration curve at 203 milliliters is going to be taken as your endpoint right here. And that's that 203 right there. All right, we'll go ahead and start up here next time. Oh my God, I am going slow. That's not good.